Good afternoon, friends. I, Professor Suprit Margi from SD Balakundi Institute of Technology, would like to solve an example with the center distance for design of helical gear. As we all know, helical gear is nothing but a gear wherein the teeth are inclined at an angle known as helix angle. The given example is like this. Design a pair of helical gear with the following data. Center distance is 400 mm, power is 80 kilowatt, speed of the pinion is 720 rpm, whereas gear ratio is 4:1. The data handbook which I have referred is K. Madhavan and Balviredi 4th edition. Given speed of the pinion is 720 rpm, center distance C is 400 mm, whereas power P is 80 kilowatt. Now we all know that the velocity ratio given is 4, which is equal to speed of the pinion divided by the speed of the gear. Now speed of the pinion is given as 720. Speed of the gear is unknown, and when we equate with the help of a velocity ratio, speed of the gear comes out to be 180 rpm. Center distance C is equal to 400 mm, which is given. Now diameter of the pinion plus diameter of the gear divided by 2 refers to be the center distance. Therefore, by substituting the values, velocity ratio is equal to dp dg divided by dp, which is equal to diameter of the gear divided by the diameter of the pinion, which is equal to 4. Therefore, diameter of the gear is equal to 4 times the diameter of the pinion. Center distance C is equal to 400 mm, which is equal to diameter of the pinion plus 4 times the diameter of the pinion, that is nothing but the diameter of the gear. Therefore, diameter of the pinion comes out to be 160 mm. For the diameter of the gear, we can calculate it as 640 mm with respect to the center distance formula. Okay, assuming 20-degree full depth involved and helix angle assuming to be 20 degree. From table number 12.4b from your data handbook, take number of teeth on a pinion or Z1 is equal to 18 to avoid the interference of the pinion. Now Z2 will be equal to velocity ratio multiplied by the number of teeth on the pinion, that is number of teeth on gear, which comes out to be 72. Formative number of teeth in case of helical gear, it is required to calculate the formative number of teeth. Therefore, formative number of teeth is given by ZE is equal to Z divided by cos cube beta, which is available, the formula which is available from the data handbook. For pinion, it comes out to be ZE for formative number of teeth for pinion, that is ZEP, it comes out to be 18 divided by cos cube of 20, which comes out to be 21.69. Similarly for gait, ZEG, which comes out to be 72 divided by cos cube 20, that comes out to be 86.77. Now for 20-degree full depth involute, the Levi's form factor Y is given by 0.154 minus 0.912 divided by Z, where Z is nothing but the formative number of teeth. This is as per the equation number 12.5d from the data handbook. Therefore, we can calculate the Levi's form factor for pinion and gear separately. For pinion, it comes out to be yp is equal to, by substituting in the above formula, it comes out to be 0.1119. Similarly, y for the gear, that is Levi's form factor for the gear, it comes out to be 0.143 by substituting z. Okay, once we calculate the Levi's form factor, it is necessary to select the weaker member for the further design of the gear. Since the material of the gear is not given and even the material of the pinion is not given, from table number 12.7 from the data handbook, we can assume for pinion as steel C30 heat treated with design stress is equal to 220.6 Newton per mm square and BHL is 300. Similarly, for gear, we can select cast steel 0.2% carbon heat treated with sigma d, that is design stress for gear, comes out to be 193.2 Newton per mm square and BHN is 250. This combination we can select. Even any other combination, whichever you feel you can select, whichever you feel safe, you can select that. But we have to keep in mind that for pinion, slightly the stress must be higher compared to the gear. Even in case of BHL, the pinion BHL must be slightly higher than the gear because pinion is smaller whereas gear is a little bit larger. Okay, now checking for the weaker member for pinion by calculating the product of sigma p into yp, that whereas sigma p is the design stress for pinion, whereas yp is Levi's form factor for the pinion. that is 220.6, that is the design stress for the pinion, multiplied by 0.1119, it comes out to be 24.60. Similarly, the product of sigma g into yg, it comes out to be 27.62. From these two values we can suggest that pinion is weaker, since sigma p into yp is less than sigma g into yg. Therefore design is purely based upon pinion. Now once before starting for the design, we need to calculate the tangential load. Tangential load is given by ft is equal to 1000 pcs divided by v. This is as per the equation number 12.7a from the data handbook, where cs is the service factor, that we can assume it as 1.25 from table number 12.8 from the data handbook, assuming as a steady load for 24 hours per day. Now p is equal to power, that is given as 80 kilowatt. The values in the equation ft. Before that, v is unknown. V is nothing but the velocity. Velocity is given by pi d1 n1 divided by 60 into 1000. Since the design is based upon pinion, we can substitute the diameter and the speed related to pinion. Pi into 160 multiplied by 720 divided by 60,000, that comes out to be 6.032 meter per second. Now substituting the value of P, V and Cs in the equation, in the above Ft equation, that is tangential load equation, Ft is equal to 1000 into 80 into 1.25 divided by 6.32032. It comes out to be 15,822.78 Newton. Now after calculating Ft, that is tangential load, the next part is we need to go for the calculating the module. As we all know, the Lewis equation is the basic equation which is used for calculating the module in any type of the gear. It may be a spur gear, it may be a helical gear, or else it may be a bevel gear. Now from Lewis equation, Ft for helical gear is given by sigma d into CV into B into capital Y into MN divided by CW, which is already present in your data handbook. So where sigma D is 220.6 Newton per mm square, CV is 6.1 divided by 6.1 plus V, that is equation number 12.25b from your data handbook. By with since V is 6.032, we have to select this value, that is 6.1 divided by 6.1 plus v, that is a velocity factor. Now substituting the velocity v is equal to 6.032, we are getting cv is equal to 0.502. Okay, cv is a velocity factor, whereas b is a phase width. Capital Y is nothing but product of y into Lewis form factor, that is y, whereas mn is normal module which we need to calculate it, and whereas CW is a wear factor. Now coming to for the phase width calculation. Phase width is given by 1.15 times the pi into m divided by sine of beta. This is as per the equation number 12.23b from the data handbook. P is equal to 1.15 pi into m divided by sine of 20. It comes out to be 10.56 times the m. Whereas capital Y is pi into y, that comes out to be pi into 0.111 times the 9, which comes out to be 0.3515. Whereas Mn is a normal module which is nothing but module multiplied by the cos of beta, where beta is a helix angle, m multiplied by cos of 20, which comes out to be 0.9396 times the module, that is m. Okay. Now CW is nothing but the wear factor, which is being selected from table number 12.21 from your data handbook. Substituting all the values, that is phase width V, capital Y, Mn, CW, Ft, as well as the design stress in the Lewis equation, we are getting m is equal to 6.8 mm. Okay, now recommended module nearer to this 6.8 mm, recommended module from the table number 12.2 is nothing but m is equal to 7 mm. Okay. After calculating m, it is required to check for the dynamic load and wear load. Now checking for dynamic load, Fd is equal to, we are having the formula Ft plus K3 into V into C into B into cos square beta plus Ft into cos beta divided by K3 into V plus C into B into cos square beta plus Ft. This is as per the equation number 12.26a from the data handbook. K3 is given as 20.67 for SI unit from the data handbook. It is required to calculate the C in this. Remaining all, whatever the beta, Ft, V, all are being calculated. It is only required to calculate the dynamic factor C from in the above equation. Okay, for m is equal to 7 mm, from table number 12.13, for m is equal to 7 mm, module is equal to 7 mm, assuming the class 2 gauge, take E is equal to 0.0353 from the table number 12.13, and from table number 12.12 for the steel to steel gear combination for 20-degree full depth involute. If E is equal to 0.03, C is given as 343.3. Therefore, for E is equal to 0.0353, we need to calculate the C by interpolation formula. 0.0353 multiplied by 343.3 divided by 0.03, which comes out to be C value as 403.9. Similarly, B is nothing but 10.56 times the 7, that is face width, which comes out to be 73.92 times the mm, or 73.92 mm. Now substituting all these values in the equation number 12.626a, as we all know, that 20.67, it is nothing but K3 is nothing but 20.67, whereas B is nothing but 6.03, C is nothing but 403.9, and B is equal to 73.92, and whereas beta is the helix angle that comes out to be 20, substituting the values, and whereas FT is 15,822.78, substituting all the values, we are getting FT is equal to 16,015.7, which is much greater than FT. Hence, the design is safe for dynamic load. Similarly, we need to check for the wear loader. Fw is equal to d1 bqk divided by cos square beta. This is as per the equation number 12.26c. Now q is equal to 2 times d2 divided by d1 plus d2. This is the value of which is given from the data handbook. Therefore, 2 times 640 divided by 640 plus 160, q comes out to be 1.68. To find k, D1 is nothing but the diameter of the pinion, B is nothing but the face width, Q is nothing but 1.68, which we already calculated, beta is 20 degree, it is required to calculate the K. K is nothing but the wear factor, which we need to calculate from the table number 12.16 from the data handbook for steel and steel combination, and 20-degree full depth involute for BHN is 300 and 250 for the pinion and the gear, K is equal to 1.108. Substituting the values, we are getting 160 multiplied by 73.92 multiplied by 1.68 multiplied by 1.108, which we are calculating from, which you are selected from the table number 12.16. We are getting the wear load as 24,932.7, which is much greater than the dynamic. Hence, the design is safe for wear load also. Therefore, the suggested BHN are BHN is equal to 300 for pinion, BHN is equal to 250 for gear, and take module M is equal to 7 mm. This which is required for complete design of the gear, helical gear. Now, therefore, lastly, we need to calculate the helical gear proportions from table number 12.20. For beta is equal to 20 degree, addendum is zero point 0.7 times the module, which comes out to be 0.7 times the 7, which is nothing but 4.9 mm, whereas clearance is 0.157 times the module, that is comes out to be 1.099. Thank you. Stay home, be safe.